Yo, yo, yo! Welcome to my channel, guys. Today, I would love to talk to you guys about something extremely interesting and important at the same time. Which would be, like the title suggested, implicit differentiation. Right. I know that all year 11 student, starting from year 11 Maths B, you guys will be learning something called calculus. Some strange calculation method developed or invented or discovered by Lebesgue and Newton back then. Right? They're both two great mathematicians, right? Amazing people. And most of the year 11 and year 12 student in Queensland, right, that I have come across with, right, I'm not sure about in other states of Australia, but in Queensland that I have come across with, they've been told, or they've been doing, or they've been learning something what we called explicit differentiation. Now, what I mean by explicit differentiation. So, explicit differentiation. Differentiation. What I meant by that is just that explicit, oh my god, the word, explicit differentiation is having to derive something like this, right? This could be, x squared plus x plus 2 or whatever. So explicit differentiation is deriving a function or equation that showing y on one side of the equation and the rest on the other side. Of the equal sign, right? So that is what we call an explicit differentiation, deriving something, deriving y equal to something. Right? It's showing you explicitly, the y is being shown explicitly there. Right? You don't have to find it. It's not covered. It's not accompanied by anything. It's just y by itself. And that's what we call explicit. And give you give you some other. Let me give you some other example. And let's just say it's x squared, the normal the normal function for a circle. Right. Now, this particular equation is in the form of implicit. Right? Because first thing, y is not by itself, right? Something is alongside with y. Something is on the y side. He's not alone. He's not a loner anymore. So this is what we call implicit. Implicit. Simply saying that y is not by itself. Y is not obvious. Y is not alone. Now, normally, when the year 11 and year 12 student, when they approach this and they were asked to derive this with respect to x, right? When they're asked to derive it with respect to the x, they do the following. So they will rearrange it, make the x to go to the other side, right? And then square root it. Square root the other side to make y, right? To make y by itself. So the year 11 and year 12 student has been taught to rearrange the equation, right, to make y the subject, right? You heard that a lot, to make y the subject. So we are changing it from an implicit form back to an explicit form. So we can differentiate it, derive it, right? And then we go, deriving it, we just go dy dx. Now, really hope you can understand this particular expression, because I know some teachers don't explain this. They just use y dash. I know they are equal, but you need to know y dash is differentiating y with respective to x. Okay? Alright, so and then whatever you do to one side of the equation, you do it to the other side of the equation. Right? To make it equal. Right? So the reason I'm doing this, I'm showing you this particular step, is that lots of teachers do not show this step to the student. The student is just learning, or I wouldn't even say learning, the student is just computing the derivative without understanding what is actually happening to the equation. So this is actually what's happening to the equation, dy dx. So differentiating y with respect to x is equal to differentiating root 4 minus x squared with respect to x. Okay? So, and then we will go on to derive both sides. So this is what the year 11 and year 12 will do in Maths B will do. And that's nothing wrong with it. That's fine. But they will come across, all right, and every now and then they will come across something that they cannot rearrange. For example, I'll write something. I'll write down there. Okay, you can try to make y y the subject on this one. Right. Okay. Now, if I want, if your teacher tells you, go ahead and differentiate this, your first instinct would be, okay, let's rearrange to make y the subject. All right. But the biggest problem in this case is that it has y on both sides. All right. You got on the left hand side there's a y cube, and on the right hand side there's y. Right? And doesn't matter how you rearrange it, you still get a y on both sides. Right? So how are you going to differentiate this? If all you know is explicit differentiation, you can't. Well, maybe you still can. I don't know. I can't. As a year 11, as a normal year 11, year 12 student, I don't think any of them, Maths B student, I'm not sure about Maths C, Maths B student, they were just stuck, right? Well, but then again, and then some of you would say that, well, we don't need to know this, right? It's not on the exam, and now that is what I hate to hear. You are learning for your own benefit, for your own knowledge. Wouldn't you want to find out? Wouldn't you want to know how to do this? Wouldn't that be better for you? Wouldn't knowing how to do something like this, or knowing how to do implicit differentiation, wouldn't that give you a better advantage in your exam or even in your life? All right, who knows what you will come across in the future? But I wouldn't go down that path, and I could argue with you all day long. But what I'm trying to say is, the more you know, the better for yourself. I don't know, quite frankly, I don't know, would this help you in your exams? I couldn't give you a definite answer, but what I can give you an answer with, what I can definitely give you an answer is, it will help you as an individual. You can do more with this extra piece of information. So I really hope you can watch this video and learn something extra, giving you a bit of more of an edge, out in the competitive world. Because you might think your school don't need this, or your classmate, no one is the whole school, no one's the whole year 11 or the whole year 12, no one's learning this. It's not needed. But what about the school across the road? What about the school in your next suburb? What about the school in your in the next city? Right? When you come out to the real world, you're going to be facing them. They are your actual competitor, right? All right. Without going down that path, I hope I make the message clear. Okay, so let's go back down to back to maths. All right, so you can't do this. You can't differentiate this particular equation with explicit differentiation. So you have to use implicit differentiation, or at least we're making it way easier. All right. Remember, both way, explicit or implicit, they are just differentiating. All right, they're just differentiation. We are still finding the the derivative. Okay, so let's make another example. All right, let's go back down to just this, something easier, like that. All right. So now I know some of you smart people would say, well, I can make the y as a subject on this one, right? You can just do y cubed is equal to 5 minus x cubed, and then y is equal to cube root of 5 minus x cubed, and I can differentiate that like that. Of course you could, and we are going to do that. We're going to differentiate this particular equation both ways. We're going to differentiate it implicitly, and we're going to differentiate it explicitly, just to show you that they are the same, and you can decide whichever is simpler for you. All right. So let's differentiate. Okay, let's differentiate. Should we do it? Would you guys like to do it the old way first, or the explicit way, or the implicit way first? I know you can't answer me, so I'm gonna be a dictator this time. I'm gonna start with the new stuff first, which is the implicit. All right. So having a look at this, x cubed plus y cubed equal to 5. Right. The first thing is I will differentiate both sides with respect to x. All right. So I will do this. Differentiate this. With respective to x, and to make the equation remain equal, whatever you do to the left, you do it to the right. Yeah, makes sense. All right, now let's do the right hand side first, which is extremely easy. What is the derivative of 5 with respect to x? Now that is just like asking you y equal to 5, right? What is y dash? Excuse me. Obviously, it will be 0, right? It's easy. So same. In this case, it will be 0, right? Because that's what it is. Now, it's a bit more interesting on the left-hand side. Now, I wanted to show you these things. I want to break this down. I want to distribute the derivative sign into each of the variable. So I want to break it down into this. I want to do this, and then plus this. Right? So I just split it, the expression into two parts. We can do that because it's an addition in the middle. Because this addition in the middle, we can split it. Okay? So let's do the first part. Now that part is easy. Right? We're differentiating x cubed with respect to x. So that is the same as y equal to x cubed. What is y dash? Right? It'll be 3x squared. Yeah, no brainer. All right, so we get 3x squared plus this. Now, and then we have the 0 in here. Now, this is the interesting bit. We are differentiating y cubed with respect to x. Now, there is there's no x in there, so we can't just do what we just did. And there's no constant in there, like the 5. Because it's not a number. Y is a variable, right? You can't just go, oh, take the number away and just put 0 there. It wouldn't make sense because Y is a variable. All right. So now, oops. Now, here is what we need to think back. All right. So you have to understand Y is a function of X. Okay. Y is a function of X. And we are trying to find the derivative of Y, right? But Y is a function of X. Now, if you understand this bit, this will just become like a chain rule. So let's say, for example, we got something like this, something you guys are more familiar with. Right. If we go Y equal to this, right? So Y is a function of this. It's a function of X, right? Whatever this is. And in here, Y is also a function of X. All right. So what do you do down here? If I was to ask you to differentiate this, what would you do? You will go Y dash will equal to, you bring the 2 to the front, right? Oh no, let's raise that to a little bit higher to reduce confusion. Let's just go 5. Okay. So we bring the power to here, down here. All right. Whatever inside the bracket doesn't change. And then at the end, we haven't finished yet, at the end with the multiply by the derivative of the inside, right? Which is 6x 6x plus 6x, just 6x. All right. Now, going back here, now Y is a function of X. And if we got this particular format, we can do the chain rule, right? The derivative of the how I remember is the derivative of the outside multiplied by the derivative of the inside. All right. So now, if you can see it, aren't they the same? Y is a function of X. All right. And now this function of X is raised to the power of 5, and Y is raised to the power of 3. This is just the same thing as a chain rule. So we can literally do the same thing, just like we did here. So what we will do, we'll bring the power in front of the Y, right? Will give us 3Y, right? So the Y is just like the bracket here. It doesn't change. Remember, Y doesn't change, right? And the power, I forgot here. The power decreased by 1, right? That's to the power of 4, right? And what do we do at the end? We multiply by the derivative of the inside the bracket. Now, since I said that the Y is just the same as the brackets here, or whatever we got inside the brackets, the derivative of that Y, of that thing, of Y, isn't that just dy, dx? Yeah? Because it's Y. Y is a function of X, right? Or Y is the same as the brackets. Now, we just like the chain rule. Oh, sorry, this would be a 2. Sorry, this would be a 2, my bad. So just like the chain rule, we bring the power to the front, right? And then the power is reduced by 1. And then we multiply by the derivative of inside the brackets. And this, in this case, the derivative of Y. And the derivative of Y with respect to X will be dy dx. Yeah, that's what we want. That is what we want. The whole time we are doing this, we're trying to find dy dx, which is the derivative of Y with respect to X. We got it. Okay? What we have to do now is to make that the subject. Yeah? We have to make dy dx the subject now. And now that is just easy. So we move the 3x squared to the other side first. So we go 3y squared multiplied by dy dx is equal to negative 3x squared. Yeah? And then we divide both sides by 3y squared. So we get dy dx finally is equal to negative 3x squared divided by 3y squared. Right? And the 3 cancels. Oops. So dy dx is equal to negative x squared over y squared. And now, some of you might say, look, you got stuck here. You got y on that side. It doesn't work. But remember what we've been saying. Y is a function of x, right? So you can express y with x's. Yeah? Yeah? So let's go back to the very beginning. Very beginning. Right? We got this. We got this equation here. X cubed plus y cubed equal to 5. Right? So, we can actually use this. This side. So if we make y the subject, like this, right? That is the expression of y in terms of x, right? So we can literally put this bit in, back in down there, right? And that is just, oops, hold on. And that is just whatever that is, square, okay? So that is just the cube root of 5 minus x squared, or square, right? Because that is what y, that's the expression for y. And y squared is just that whole thing square. And if you want to make it nicer, make it look better, that is just negative x squared over, what do you call it? So this is 5 minus x squared to the power of 3 over 2. 3 over, oops. Cube root is just 3 over 2. No. Cube root is 1 over 3, sorry. 1 over 3. What am I thinking? Right? And then to the power of 2. Right? And now with our index law, all right, we can just multiply the power. It just becomes 5 minus x squared to the 2/3. Yeah, and that's it. All right, that's the derivative. Okay, now let's just do it the explicit way and see if we get the same thing. Okay, so let's go back there. Let's go to here. So we're going to divide dx, or we can call it y dash, whatever you want. So what do we do now? We should change this in the form of as the form of power. So 5 minus x to the power of 3. Oh, was it 3? Did I write 3 here? Oh, I should write 3 here. My bad. Okay. Now, so that can be written as 3 minus x cubed to the power of 3 minus x cubed to the power of 1/3. Right? Now, to do that, to derive this, we use the chain rule, right? So it's 1 over 3. Right? And the bracket doesn't change. Whatever inside the bracket don't change. Right? And then we multiply by the derivative of the bracket, which would be negative 3x squared. Right? And then, oh sorry, this is a so the power is -1, so it becomes negative 2/3. And then that is just negative 3x squared bracket 5 minus x cubed to negative 2/3 all over 3, right? The 1/3. And now the 3 cancel and remove the we don't want to keep the index as a negative, that the power as a negative. We want to move it to the bottom, to the numerator. So it's just negative x squared over 5 minus x cubed to 2/3. Voila! That is the same as that. Right? Right? So it works. Implicit derivative works. I know you might think this particular example, it took longer steps and things like that, but it's just for this particular example. for other example, sometimes you really just can't differentiate explicitly. But now knowing that to derive something like this, is just like a chain rule, right? You bring the power to the front, and then the power -1, and multiply by the derivative of the inside. Knowing that will give you the same answer as differentiating it explicitly, right? Isn't that amazing? Knowing that is actually much more powerful than much more useful than you think. Right? Later on, I'm going to pose a question up, which is a modeling which will be a modeling question, and it will require you to understand implicit derivative or differentiation. Right? So have a crack at this particular question. All right, and I will do the solution in the next video to show you that how. Now, I'm giving you a hint. You have to use implicit differentiation to find out the answer. All right. So I'm just trying to show you that knowing this extra piece of information is so powerful that it just allows you to do so much more, and calculus actually becomes so fun. I know to some people, it might not be fun, but to me, at least, it opened my eyes. If I would have, if I known about this, I would have been the duck of the school. I would have been that, but I'm just joking. But trust me, guys, knowing this particular piece of information, it will open a lot of path for you guys. All right, let me just fool you out a little bit of example here. All right, so let's do this. Y equal to 5 to the power of x. Now I want you to differentiate that. Yeah, I want you to differentiate y with respect to x. How would you go? What's your first step? Now this x is to the power, right? This x to the power, right? How are you going to do it? Yeah, I know. I'm not gonna get an answer here. I don't know why I'm waiting. But some of the textbook will have this particular example in here, right? We'll have this particular example. Let me go find the actual rules that was imprinted in the textbook for you guys. All right, give me a second. All right, I think what I found in the textbook is something like this. So it's given to you like a rule. It's given to you that y equal to a. If y equal to ax, then y dash is equal to ln a multiplied by ax. All right, I think that's what the text was given. Now, I want you to try to find the derivative of that and prove that this rule is right. And I'm not saying it is wrong, but I wouldn't call this particular rule given by the textbook perfect. All right, and if if you actually do this yourself using implicit derivative, hint, implicit derivative, you will understand what I mean by this rule provided by the textbook. This rule is imperfect. All right, and I will show you the answer in the next video. Have a crack at it.